Good morning. What I'm going to do today is look at the topic, the water cycle and water insecurity, and I'm going to look at section 5.2a. So if we just click on that and break that down, so 5.2 is considering the drainage basin as an open system. So if you remember, we've discussed the differences between an open and closed system. And an open system means matter can transfer in and out, unlike a closed system. In this case, we're really talking about water. So we've got a set of linked processes. So we've got to understand the hydrological cycle is a system of inputs, flows, and outputs. The inputs, precipitation, precipitation is the main thing. Flows are where the water transfers from one store to another, movement. Then the outputs, where we lose water or matter to the system. And you've got in brackets the ones you have to know about. Right. Here you've got the key ideas for the whole of 5.2, which I'll not read to you, but it tells you exactly what they expect from 5.2, and it's all studying now the drainage basin rather than the global hydrological cycle. So you're going from a closed global system to an open drainage basin. To begin with, a lot of A-level candidates don't know a great deal about place knowledge, and I'm sure that's not you, but if you want to test yourself on that, there's a little map here. You might want to see how much of these maps you can label. So you've got the different rivers, actually a few cities as well, which you definitely should know, and seas, and then world rivers, which also need labeling. Anyway, feel free to play around with that. You'll never be tested like that in the exam, but it's good to have an idea where these things are. Right, first bit then, the drainage basin. So like we keep emphasizing, it's an open system. And the open system, the inputs, processes, and outputs exist inside the drainage basin, sometimes called the catchment. So we have, around the drainage basin, a watershed. And that's this dotted line all the way around here. Now I like these 3D diagrams because they show how the water travels through this system. So if you imagine, essentially, when rain falls, let's say a raindrop falls there, where the red dot's just been placed, it's got to flow downhill. So this particular raindrop, under the influence of gravity, remember conversion of gravitational potential energy to kinetic energy, will flow downhill towards this particular river. It's not going to flow down to another river next to this one, the catchment along, or the drainage basin next to it, because it's going to flow downhill. It may well evaporate and never get to that river, or enter a water store for a long time, but if it's going to go to a river, it's going to head towards that one. So that's what we mean by the area of land drained by a river. That is what a drainage basin is, and its tributaries. So always the way to look at this is the whole of the United Kingdom, or any country, is divided up into drainage basins, and they tessellate. There's no gaps. If you're on the top of the watershed, you look towards one river, it will be downhill. If you look towards the adjacent river, that will also be downhill. So the watershed is going to mark, logically, it's got to mark the highest area of land in that particular area, which is what this is showing. So the source of the river up here was, rivers have lots of sources, but the high land up here, the water, when it falls from the sky, it will flow downhill towards this particular river. But equally, it will do that from here as well. So there'll be areas within this which is higher than others, but wherever the watershed is going to mark the highest land in that area and divides two drainage basins. So when we talk about the open system, we're talking about how water flows in that area, in that drainage basin, the area drained by a river and its tributaries. If you look in the Hodder textbook, page 5, or the Frost textbook, page 26, it shows this quite well. So you might, to make sure you've understood the drainage basin and the different parts of it, there's a little word search here. which goes through the different bits. You just need to know the different words. So feel free to have a go at that. One of them you'll probably struggle with, which is A to cross, I think, which people struggle to get, but I'll give you the answer at another point. Just to make sure you know the key terms. Again, obviously you won't have a crossword in the exam, but you do need to use the key terms. Now, most of the key terms are written around here, but if you were to look in the textbooks as well, you've got a drainage basin given, I think it's page 26 of the Frost textbook, a similar kind of diagram, and you've got different the different labels there. Also in the Hodder textbook, it has a more diagrammatic drainage basin and the different flows given there as well, but I don't think that's quite as good. So, typical exam question, a bit like the previous one we've done, but explain why drainage basin is an example of an open system. So once you've done the next bit of this, and you've got your head around how water flows through, that's the kind of thing we're aiming at. So one of the ways and places to start, and the best place to start on that, will be Frost on the top of page 26, which starts you discussing that. But from the previous work we've done on open systems, you should be able to demonstrate this. So like it says here, you've got to understand what a system is, and when you've done this bit as well, you'll know a drainage basin has got inputs, flows, which are the processes in this definition, and then outputs. So an input of precipitation, for example. A flow could be, let's get one you might have heard of, infiltration, moving from soil moisture storage to, from the surface storage to soil moisture storage. And then you've got an output like evaporation. If you remember, a flow moves water from one store to another. So in that particular case, it's going from surface storage, like could be a puddle, could be a lake, sinks into the ground to soil moisture storage, which is the water stored in the soil. So we can demonstrate it is a system, but also we have inputs, which is your precipitation. So that's going to come from elsewhere outside our watershed. But also we lose water, we have outputs because the water flows to the sea, for one example, or it evaporates out of the system. So matter is transferred to another system, another drainage basin possibly. So the second little bit of this is looking at how the hydrological cycle exists in the sense of its inputs, flows, and outputs, which is straight from the wording of the spec. The first thing you've got to do here, again, is make sure you know all the words in that diagram. Now, these are discussed in several textbooks. I like the WAF textbook for this, the big white textbooks. It's got the same diagram there, but then it explains each word in detail. And then it goes on to looking at different factors that affect the flows through here. But you need to know each one. Some of them you'll have heard of, like evaporation, transpiration, probably. Others you won't, like percolation and infiltration. What's the difference? So what we've got to do is first know what these words mean, then know how they are linked. So for example, precipitation, water falling from the sky, some of it is intercepted. And when you read about this, that's just when trees literally intercept or block the rainfall. It hits the tree first. Some of the rain never makes it to the ground. It will just evaporate off the trees. That is not transpiration. That's just evaporation off the leaves. So it goes straight back out here and evaporates. Some of it will flow down the stems or even drip off the leaves straight to the floor. And it'll end up as surface storage. Now, some of that could just be puddles. Some surface storage is a bit more permanent than a puddle, which might be a lake or a reservoir. Now, that water, if you imagine a puddle on a forest floor, will start to sink into the ground, which is infiltration. Now, the speed it does that will depend on all sorts of things. For example, if the soil is really sandy, infiltration will go really quick. If you think about pouring water onto a beach, it sinks in really quick. If you pour water onto a really clayey soil, the water tends to sit on the surface a lot more because clay doesn't have as many air holes in it and they're a lot smaller. Well, it actually has lots of smaller air holes, but because they're smaller, it takes longer for the water to sink in. Ultimately, and on the next section, you're going to have to think about different reasons why these flows are differ. So soil type matters. But anyway, infiltration into soil storage. Now, the size of soil storage will depend on how deep the soil is. It will depend on the type of soil. Now, eventually that might sink even deeper into groundwater. So this will be dealt with in more detail later. But if it percolates down into the groundwater storage, which is deeper, and it's a saturated ground or underground, so it's completely full of water. That where soil moisture storage sits on top of that. If you get to a point where all the air spaces are taken up deeper in the ground, that's the groundwater, and it's marked. The top of it's marked by the water table. So if you pass through the water table, if you dig a hole in the ground and you go through the water table, anything underneath the water table will just fill up with water, because all the ground at the sides will be completely full of water, so it will just pour in to the level of the water table. Now, if you just go back a little bit, any water in the soil might well be taken into vegetation storage. The roots take it up. That might go up into the plants and through, I think it's the phloem and the xylem. It takes that water up to the leaves, and some of that will transpire out of the pores or stomata in the leaves, and then that will go back into the atmosphere and it's lost to the system, hence open system. Sometimes if we link evaporation and transpiration together, you'll see the word evapotranspiration, which is all explained in the textbooks too. So looking at some of the other links, soil water storage, again that's a store of water, some of that will flow through the soil. If you imagine, going back to our drainage basin, water flows downhill, so it will flow say down there. Any water in the soil underground on that slope will also flow downhill, but inside the soil. And that, I'll just close that, that is throughflow. And that eventually will also end up in the river. So you've got surface flow and throughflow. The surface flow is going over the surface downhill, throughflow is deeper. The groundwater does the same thing and eventually ends up in the channel too. And that's the slowest. What tends to be, as a rule for all of this, as you go deeper and down underground, everything reacts more slowly and moves more slowly. So this is fastest, it gets to the river fastest. This is a bit slower, and it gets to the river a little bit later. And this is more constant, doesn't change as much in rainstorms because it's deeper. But this tends to maintain the very base flow of the river, the lowest it can go. If the river level flows below the water table, water will pour in from the sides and maintain it, so it will stay at the water table. So in the summer, when it gets really dry and you haven't had much rainfall for a while, the river levels might get very low, and they might be just about being supported by the base flow, which is water which was deep underground, still pouring into it from the sides. And then all that ends up in channel storage, but it doesn't store there very long. It flows and eventually back to the sea, which is an output. So I think I've covered all of these things on here briefly. It's your job to have a look in the textbooks and read up on those, and you could do a little bit of online research, but don't go mad, to make sure you really understand each one. But if you go back to the objectives, the B asks you to look at how inputs, flows, and outputs, their importance and how they link. So, for example, when you look at these, you need to know how they work first, but if you change, zipping back to this, the climate of the soils of the vegetation, if we change the vegetation, say, let's say we go from an oak woodland to a farmland and we have crops and cereals, the amount of interception will fall. If you change soil type, you'll change infiltration. So what it's saying is, as you change different factors in a real place, it's going to change all the other stuff in that drainage basin. One of the things you can do for your field work is look at how big a change one factor causes. So for example, we've had people in the past study precipitation patterns and the impact on infiltration ultimately. or the impact of soil differences on infiltration and so on. How much does interception vary with changing vegetation? So these are things you can actually study for your fieldwork too. A lot of people do that, and it works very well. Right, the last little bit on the spec mentions, or in terms of the inputs, mentions precipitation type and pattern. So what I would do with this is focus on how the precipitation types might alter the hydrological cycle. In the spec, if you read it, at the top of the sheet, it has patterns, then you've got types. So the patterns we'll talk about in a minute, but the types are orographic, frontal, and convectional. So convectional is when basically the sun heats the ground, air rises, cools, condenses, and it rains. But the key thing with that one is it's really intense, so it's a lot of water very quickly, thunderstorms. One way of thinking about that, if you get a lot of water all at once, the soil can only absorb so much water per minute. If it falls very quickly and all at once, you tend to get a lot of water left on the surface because the soil cannot absorb it as fast as the water's falling, and it can lead to lots of surface runoff. So that's the key kind of idea with that one. Frontal rainfall, well, the key with this one is you get two fronts going over the say over the UK. These can be as big as the UK. A warm front, which tends to bring drizzle, and a cold front, which seems to the cold front tends to bring heavier, more intense rainfall. Not as intense as convectional, but it does bring more intense rainfall. So you like to get more surface runoff. Orographic rainfall is where you've got hills, or it's relief rainfall you'll have done in lower school. Hills cause air to rise, and then it causes it to rain. So, for example, the west of our country tends to get a lot of rain coming off the Atlantic. The air comes off the Atlantic, rises, cools, condenses on the hills, and rains. That can bring a lot of drizzle, but it also can mean after that hill it gets drier, and that can have an impact because the west of our country, for instance, gets a lot more rain. The soils tend to be full of water all the time, particularly in autumn, which means that you end up with more runoff. So what we've got to do is, one, just have the basic idea of how these different rainfalls work, and then, and more importantly, show how they might impact on that drainage basin. So just to summarize, the convectional rainfall is really intense, so you tend to have, as a percentage of how much falls, the infiltration tends not to be able to keep up with it, which means a lot more water is left on the surface, which means there's more surface runoff. Whereas a warm front tends to bring, on the frontal rainfall, tends to bring a lot of drizzle. Infiltration is more likely to absorb more of that into the soil, which means there's less surface runoff compared with convectional. So what all it's really saying is that as you change the nature of the rain event, you're going to change how it moves through the system. Even things like, if you imagine sheltering under a tree, you get a little bit of drizzle, it might all be intercepted, you stay dry. If it keeps drizzling all day, then you're going to get water dripping down on you, and then so if the rain carries on for a longer period, you end up with interception. Interception is less effective over time, so they end up with more getting to the ground. So that's what we mean by the types of rain, and in the Hodder textbook on page 7 it shows you these types. But again, I would focus on how it impacts on the drainage basin and just have a basic understanding of how they work. Secondly, it just talks about consider patterns. Now again, when we do the next topic here, we'll look at this in more detail. But patterns of rainfall, well, if you just think of something like we get really wet winters, so if you think by the spring we've had lots and lots of rain, just think what the soils are like. They're full of water. So if they're full of water and we get more rain falling on them, that rain's nowhere to go because the soils are already full, they're saturated. So you're going to get loads more surface water. Some of it will be surface storage, some of it will run off the surface. In extreme examples, you get flooding like we've just seen recently. So it's a case of trying to think through, but not learning loads and loads of examples, but just understanding how a change in one factor, such as rainfall, can impact on the whole system. Equally, deforestation will also change the system because you're going to get less water being taken up by vegetation. You're going to get less interception. You change the soil, you change the type of rain, you change what rocks are underneath the soil. This all going to change how water flows through the system. So really, it's a case of you thinking of nearly different scenarios. So with this, the whole kind of 5.2 is about how water flows through this system. And the next two sections, the first one focuses on physical factors, and then the second one focuses on human factors. So it's getting your head around how they impact on them. So the key for A is to make sure you know what a drainage basin is and the different parts, so you can talk about them confidently. And that's given pretty well in your textbooks, and that the crossword helps you remember those. Understand that this is an open system, going back to your previous notes and what we discussed earlier. You then need to make sure you know all the terms in that diagram. Some of them are more obvious than others. But the key then is to start thinking about how they're connected. So how does precipitation influence interception, and so on. And then finally, the spec focuses on precipitation as an input. So you've got to think about how, if you change precipitation type or patterns, how it might impact on the rest of the system. And the general idea is intense precipitation means the soils tend not to be able to absorb the water as quickly as it's falling out of the sky, so you end up with surface storage and surface runoff. If you get drizzle, the soils tend to have time to absorb that water, so you tend to get less surface runoff, and the ground tends to absorb more of that. Obviously, that will vary from place to place depending on what the rain's falling on and so on as well. So having an idea how these work then helps you explain the impact. So just really briefly again, orographic, air rises and cools, condenses and rains as it travels over a hill. That can cause quite long bouts of rainfall. It's not and frontal rainfall is kind of linked into that in some ways, but it's the warm air and cold air rising over each other. When you read about this, on a warm front, the warm air collides with cold air and it rises above the cold air, very like a hill. Then it brings long-term drizzle. And it's the impact of the drizzle what you've really got to focus on. Or on the cold front, it's more intense. So it's going to have an impact on how it reacts, because it's more intense, less infiltration as a percentage, and therefore more surface runoff. And it's just a case of following it on that diagram. When I was learning this, what I did was kept thinking of different scenarios and just running them through it, and trying to think of all the knock-on effects. There's a couple of exam questions at the bottom there, the type of thing you might face. Feel free to have a look at those. The part of the specimen paper is that first one. Okay. Right, I'll leave it there. Thank you.